Cool. Well, hello everybody. Welcome. Welcome to, I think it's our fourth now live webinar here on YouTube. Today we'll be talking about our new product we're excited to announce, or we announced last year, our MakerBot method. You got me, Felipe, and as well Dave Weiss is joining us, our VP of Engineering, who hopefully will be talking about a lot on what happened during the development of the machine, what are some of the features. And just before we get going, I just want to make sure that we have everything set. So if everybody's getting our audio properly, just tell Allison. By the way, if you want to enter comments, go to youtube.com/method, and then you can join the conversation, talk to us, and please feel free to ask questions as we go. So if
/MakerBot/live.
Oh, youtube.com/method/MakerBot/live.
Cool.
But yeah, if we're good to go, hopefully you guys are getting our audio and video signal correctly. So yeah, let's get started with the presentation now. As you guys know, we've been around for quite a while. We are about to celebrate our 10th year anniversary. And we have quite a range of printers during that timeline, right? We've been known for starting with very open source printers. When back in April 2009, when we introduced the Cupcake, the Thingomatic, the Replicator series, starting with the Replicator, Replicator 2, the Plus series as well, and now with the method, right? And you can see that we've been kind of moving quite a bit during those years, right? It's changed a lot, the way that we approach the technology, our available resources, and ultimately the experience that we want to provide our users. And we believe that method really takes that extra leap, right, into the professional space and allows us to offer a new product that wasn't available before, specifically to engineers, to designers trying to prototype, trying to iterate faster. We finally we think that we really crossed a very important line with this new product, which took some time to develop. So I don't know if you want to start with that, Dave.
Sure. So the engineering team and the product design team has been working for about 3 years on the MakerBot method. It represents really the first platform that we've launched since Replicator 5th generation back in 2014. It's also the first platform that we've launched from the ground up as being a Stratus subsidiary. And I think it reflects kind of the growth that MakerBot has done internally, just learnings from being in the desktop world for about a decade. Plus the decades of knowledge and expertise that Stratasys has from inventing FDM printing in the first place. So that's been hugely beneficial, and I think you'll see some of both of our DNA in this product.
Yeah, so we'll start with, we'll go through some of the high-level features of it, and we know that there's a lot of questions out there about what do we mean specifically when we say, fastest cut to part, what do we mean by the precision and the reliability of the machine, and we'll touch on each of the systems that make that happen and explain what we mean by each of them. So starting with, kind of the general value prop of the machine, right? There's three big things, right? Matching, industrial reliability and precision. That means being able to print something that actually aligns with your CAD, with your design, and that gives you the expected dimensions every time. Then, moving on, the fastest cut to part. What we mean by that is actually looking at a full user journey. So if we move on to the next slide over, we want to understand the full user journey from CAD creation to having the actual part on your hand. So we really want to optimize every single step of the development and of the printing process for a designer and engineer, whether it be by supporting multiple file types, whether it be by providing with a really fast machine, which, by the way, you'll see it in a second, but we have it back here. It's quite an amazing machine, I think, a really good-looking machine as well. And then the next big pillar on the deck is our, we call it the maximum innovation, minimum investment. And that ties to kind of the price point versus the features that we're offering, right? Many of these features were locked before for more entry-level systems, which means in order to get them, you have to pay upwards of $20,000, $30,000 in many cases to get this level of precision, this level of resolution, and ultimately the performance that we are offering with Method. And with that, we'll start with each of the systems. So we move on to the next slide over the core features, beginning with the bones of the machine. So let's start with the basics, and we'll be bringing some of the props in camera. Hopefully you guys will see a lot of it and the details of it, but here's where Dave's technical expertise will really shine.
Great.
Starting from the ground up with I would call the bones of the machine. So
Right. So absolutely. So thank you. So in designing the method, when we decided what we were shooting for in terms of requirements and bringing down a lot of that industrial capability, it became clear that we couldn't do this incrementally on our existing platform, and that's why we started on a whole new platform, from mechanical architecture, electrical architecture, firmware, even print preparation tools. So I'm going to show you some of the basically physical core features that really make this machine special. So yeah, we start with the foundation of the machine, which is the base. So we went away from a panel design, which is common in the desktop world, and we have really design made up of just 4 main components that make up the whole frame, provide XYZ alignment, as well as structural rigidity. So we start with the die-cast base. This is a die-cast metal base, CNC machined. Then extruded aluminum uprights, also CNC machined, and then a one-piece steel weldment. So this really does 2 things. So in 3D printing, we're moving around a carriage and extruders very fast. That generates forces, vibrations. We need a frame that is solid enough to absorb those vibrations and not transmit those vibrations into the part itself, because in that case it would show up as a distortion in the part, a defect, essentially. The other thing we want to do is every machine coming off the line, we want to line up our X, Y, and Z axes very well and very repeatedly, and by referencing CNC machine surfaces, we can do that.
Right. So just stopping there for a second. What's the importance of having the 3 axes perfectly aligned on the machine?
Sure. So most objects that you print are essentially a combination of polygons and arcs, right? Mm-hmm. So simple polygon cube, right? So you can see in these printed cubes we have, very sharp corners and edges.
Really close.
Sure. Okay. So if you look at the surface here, you can see the surface finish is quite nice. We call this vertical surface uniformity, and it's just how well every layer stacks onto the layer before it. And you get a very smooth surface, both on the top and on the sides.
Right.
The other thing we do is hold really tight perpendicularity tolerances. And so if this is X, this is Y, and this is Z. Okay, that's important, especially for mechanical assemblies. Mm-hmm. So we have some prints here that have a 50 micron gap between the mating surfaces. And we printed these out without any adjustment, balanced print mode, and we have like a nice slip fit here between these parts. And really, if there were any, if there was any like surface finish issues, mm-hmm.
Raised radii,
these just would not be able to be assembled.
So we have a few pictures. If we move on to the next slide over, showing specifically the detailed shots of what Dave just said, right? Mm-hmm. And you can see the picture on the right. That's a desktop machine. Sometimes it's hard to tell, at a glance. Specifically, this we printed 2 different cubes, and you can see how on the left the method print. It's actually giving us that very fine line, very straight lines across the print. That's basically this cube, actually. And on the other hand, you see that little noise, right? That continuous waviness. That comes from, I guess, what you were describing, right? The rigidity of the frame and the fact that the machine is vibrating a little bit, just enough to distort each layer mm-hmm. And not align them properly.
That's right.
So that's really important, especially when you consider the fact that many desktop printers claim that they can print at these lower layer resolutions, right? That they say like 40 microns or 20 microns. How do you go about that idea? The fact that sometimes it's more important to be able to print. You do need the higher microns, but, mm-hmm. or lower microns, I guess. Mm-hmm. But to align the layers sometimes is more important than the height of them.
Yeah, absolutely. I mean, So printing at like 40 microns, as you said, is just lowering the Z stage by 40 micron increments and putting out less plastic. But if you have, say, a couple hundred microns tolerance and where that layer ends up, then it kind of defeats the purpose of having that resolution.
Yeah. So if we move on to the next slide, there's another one that's really cool, and that's kind of a 3P surface that we designed here using Grasshopper and Rhino, and you can see the same idea, right? On the left, you have them over there. On the left is a desktop printer. Right. We'll bring them closer, but it's like these. Let me see, because it gets like this really nice effect. Yeah, there we go. So with the shadows of it, and it's kind of very interesting to see. But that's just the eye candy that we created. But the thing is, or what we wanted to focus on was specifically that, right? Even with these textures that are not even, and that you wouldn't necessarily expect them to be as lined up as with what happened with the cubes, right? It's still very important to keep in mind the fact that having that axis perpendicularity, having that strength and that stiffness on the frame will actually translate into a very, very, very good print and very smooth print for that matter, right?
Yes.
So if we move on, we'll start talking about like the next system over, which is it's a big one, and bear with me for a second because I'll be bringing the props here.
Sure.
So let's get started.
Yeah, absolutely. So I want to talk about the heated chamber next. A requirement was 0.2 millimeters, plus minus 0.2 millimeters, X, Y, and Z, up to 100 millimeters accuracy, and that's really regardless of where you're printing in the build volume. So we had to go with the heated chamber. I'd like to explain kind of the differences in this heated chamber versus a heated build plate versus kind of a pseudo heated heated chamber. So, back in 2012. MakerBot had the Replicator 2X. There's a heated build plate machine. We enclosed it, so it was what I would call like a pseudo heated chamber. Provides some heat, but it's really varying heat throughout your part volume, throughout your build area, and throughout your Z height. So you're hot on the bottom. Your part sticks. The bottom of the part is flat, but as you work your way up, essentially the part will warp in different ways because you have a different environment, and you just can't really control that. So what we're doing here is we have dual U ducts on both sides of the build volume. We're pulling in cool air and pumping out hot air and creating this level of very high accuracy temperature region right at the build plane. That lets every layer throughout this part be built at the same environment and lets the part slowly cool. So this is an example of a motor housing that we printed, and yeah, thank you. So what we see here is the bottom is flat, right, and that's achievable.
The one on the back.
Sorry?
So if you go closer to that one.
Oh, got it.
The guys are over there.
Okay. So the bottom is flat, and okay, that's achievable even with a heated build plate without a chamber. But then if we flip this around, the top is flat also, even for like these cooling fins. And that is something that you really can't do unless you control every layer. Aside from part distortion, it also gives you consistent and improved layer adhesion. So your strength of how well your layers bond to the layer below it is also increased with the heated chamber.
So one thing that I've been hearing a lot of in many comments, and we follow all of the comments out there, different blogs and publications asking about what why did we skip doing the heated build plate, right? Why do we think that the heated chamber is better than build plate, and specifically on the first layer, because we know that many printers, especially desktop systems, use a heated build plate as a way to make the plastic really adhere on the first couple of layers. What happens when you don't have that and you have the active chamber instead?
Sure. So an object like this printed with an open machine, or even likely an enclosed machine with a heated build plate, you'd have like a glass smooth surface on the bottom, because your build plate is actually above the TG of the material, the thermal gradient. So
what do we mean that?
So
everybody together.
Sure. So it means usually below the melting point of a material, but you're at the point at which the material deforms at that temperature. So your material kind of bonds itself really well to the build plate. but then the differential between the temperature at which you extrude and the temperature at which you extrude on just gets greater up here. So if you're, say, subject to ambient air here, like 17 degrees C, but you're extruding your plastic at 220 degrees C, that plastic's just going to want to work, and it's not going to want to adhere as well to the layer below it. So basically, if you printed fins like this, the entire Z stage, you would have more and more warping as you work your way up, and that's really not possible to compensate for by, say, like scaling a CAD model, because you just don't know the environment.
Yeah, I think it's really interesting, especially when you think about the fact that claiming a specific dimensional accuracy, it's not the same to say that you have it as somewhere, meaning close to the build plate, as to have it across the full build volume.
Right.
So being able to respect the dimensions everywhere where you go, so that, you know, as you were saying, like every single fin here is like dead on straight, instead of just having a super clean, which we've seen a lot, right? You see a lot of desktop printers that have the glass surface, and it does come really nice and flat and smooth on the very first layer. But if you know your part being made out of thousands of layers, it's important to keep that flatness in each of them. So yeah, that's pretty cool. Then, what are the temperatures that we usually, or that we have available in the heated chamber?
Right. So it's variable based on the temperature, based on the material that we're extruding. So for like MakerBot Tough, we will run a 40 degree C chamber, which just, and we really had to do some experimentation, but we found that like plus minus 5C really matters. So you set it per really the thermal gradient of the material. So, you know, we're working on PETG. PETG is a little warmer, so we the thermal gradient's higher. Thus, we just raise the chamber automatically when a user chooses to print something in PETG.
Great. And then, since we have this really nifty prop here, I also wanted to talk a little bit about another component here in the chamber. I would call it more of a user-friendly component, which is our removable build plate. So here, actually, let me get rid of the prop. So this is our build plate, right? And then it's just held back magnetically to the actual, how do we call it, like the C stage here on the machine?
Yeah, I mean, we call it internally the backbone, but it's just your plate in that you build upon. So this is reusable. So it's a reusable polycarbonate surface mounted to spring steel with an overmold. And again, it's magnetic and it's very, very flexible. So the level of on the Replicator Plus does have a flexible build plate, but this really is much more flexible.
And the obvious question then, you know, you just flexed it quite a bit, but how easy is it to distort that steel, spring steel?
So I mean, it's the same material that they make springs out of, so it's made, you know, it's made to do this. And we have a distribution of magnets here. So when this is put on, it conforms to the surface of the plate. So we control the flatness of this plate to very tight dimensions, and then this just will conform.
One in for everyone to see. So you see how we've got like those, is it 17 magnets here, right? That are helping to keep that real surface in place. And there's a few other features here. I think that we also want to touch on those, specifically this kind of shiny machine component. What is that, and what are we using that for?
Okay. So a big headache with dual printing in general is the alignment of your nozzles, your model and material, your model and support rather. So your accuracy will only be as good as those two nozzles are lined up to each other in an X, Y, and Z space. On most desktops, you either dial those things in manually by actually adjusting the position of the nozzles, or you run through like a calibration script, and you measure parts, and you feed back numbers into the machine. So we wanted to take the guesswork and basically all like the variability out of it by having to do these manual operations. So this is essentially a target where our nozzles will perform edge, both Z locating and edge locating. So yeah, perhaps we could break out the carriage.
Let's
show how that works.
Wait for the carriage. Let's see. So here we go.
Okay. Thank you.
This is like a more reasonable prop to have around.
Yeah. So this is our dual extruder carriage. Okay. So we have model and support, and both extruders act like a probe. So see, they're mounted on a flexure. Okay, and they have sensing through a Hall effect magnet that when there's displacement, So we run this like a probe to check Z between the nozzles and XY.
Yeah.
We also these heads toggle.
So on that note, though, this is kind of the big change between the Rep Plus series and this one is the fact that we now have the two heads, right?
Right.
And then the fact that we are using them for individual purposes, each of them, correct?
Exactly. So this is your model. So it's made for. So far, all materials that we brought to this platform use the same model extruder, and the support is specifically for PBM.
Yeah, and I like also the fact that we kept it, like a modular system where you can just interchangeably get the heads out, and I'll bring it closer so you guys can see it. But it's pretty much, it follows that same modular logic that we had in the Plus series, right?
Yes.
Where each of the heads is easily swappable, replaceable, but it's different, right? It's quite a different system.
Very different. So yeah, we could move on to the next slide is I believe the extrusion. So you'll notice this extruder doesn't look like any previous MakerBot extruder or really any other desktop extruder. So it's got a very, very long hot end. The reason for that is simply to melt a lot more plastic faster. So the cartridge heater runs the full length of this hot end. I have an extruder here that I can take apart. Yeah. So this is the hot end. This is where the material melts. Okay. So we can get a very high volumetric flow rate. We also have a gearbox, which you can see on the actual part and on the slide. So this is a 19:1 gear ratio. It lets us get about 4 times the torque that we have now, with actually a smaller, lighter weight motor.
Right.
So.
And then that's another question that I saw a lot of, and I'll keep this close to the camera so that you guys can keep on seeing it. But the question around, the fact that we're claiming a much higher material flow rate. So we do have an elongated thermal core. We do have more torque to push the filament through, but it's not enough with just the mechanical changes, right?
Right. Absolutely. So it becomes difficult. The faster you go, the tougher the controls get. Okay. Because you're trying to deposit plastic out of this nozzle very, very accurately. And the larger your reservoir of molten plastic, if you will, in here, the harder that is to control. So this is essentially like a really powerful engine, right? But you can't just drop a really powerful engine into a regular car, right? So we had to upgrade really all of our control systems and all the things that we're doing, processing speeds behind the scenes to ensure that we get consistent, accurate extrusions.
And so how does that what does that mean for my printed part? So if I'm having a higher flow, is that the direct transmission is higher speeds, better material flow? What is it come down when we're talking about the parts, the printed parts? What specifically?
Sure. So it's higher speed. Okay. So our goal was for this machine to go about twice as fast as like leading desktops, and we're there now. Okay. But the hardware on this machine gives us a lot of running room to move faster. So we're at about half the capacity of the extruder now. So through
you mean that we'll be able to later on increase the speed of it?
Right. We're not blocked essentially by the rate at which we can melt plastic.
I see.
On this machine. So yeah, it's faster, and we just have a much wider range. We can still deposit plastic slowly and very, very accurately, but we can crank that up for things like infill, where you're just adding. So infill is basically what you don't see on this part. So it's just kind of the mesh that you create to give the part rigidity
Mhm.
inside of the main form. So we can do things like that very, very fast.
Right.
And then if you want a very, very accurate small pin
Mhm.
or something, we can also do that through controls.
So one other thing that I think that it's a common challenge for all of the printers that are using this dual system
Mhm.
is the fact that as you have the two heads available for you, then you also risk them contacting the printed part,
Sure.
right? The idea that you have to actually toggle them.
Yep.
And can you talk about a little
Yeah,
bit on,
sure,
I'll hold this while you
Yeah.
describe.
So we have a bar that just goes against the side of the gantry
Mhm.
and shifts the Z position of the heads. So whichever head we're printing with is a little bit over 1 millimeter further down than the head that we're not printing with. So that prevents when you're printing model material.
Yeah.
That gets the support extruder out of the way, so we're not contacting the part and putting on a defect, and we're also not getting any like oozed material onto that part.
Right.
Mhm.
What I like a lot also is the fact that so many other printers that I've seen have sort of this home place where they have to go back and make the toggle switch.
Right.
Whereas this one is constantly traveling with the print heads, right? So you can always
Yeah,
just go to
correct.
the wall and
Right. So if this is X, wherever you are in Y space, you can go to your closest point and toggle.
And it's funny because I've seen it a lot also, like, 'cause we've been conducting a lot of print tests. That extra second that it takes you for you to get all the way back, make the toggle and come back. If you multiply it by the 1,000 layers or more that you're having, it really does add up, right? And it adds a lot of print time to your part.
Yes, definitely.
So yeah, like if we keep going, we also want to talk about some specific additional features, like the material base, right? So this printer, previously we have had some sort of open drawers in their Plus series,
right.
but now we have what we call the dry sealed material base, right?
Right. So this is our first sealed material machine. It became increasingly important on this machine, again, because of the requirements that we wanted to hit, the reliability. So plastics absorb moisture. Okay. When they absorb moisture, it causes problems in extrusion because you're heating the plastic. You don't want you don't want moisture in the plastic while you're heating it. Okay. So we wanted to control that variable, so we added these dry seal material base. So in the spool itself, there's a hub that has a replaceable desiccant pack. These are also, by the way, shipped in Mylar bags.
Okay. Yeah.
Okay. So in the bags, if you're not using an entire spool, you can store it in the bag and it will stay dry. To place this in the machine, we have a temperature and humidity sensor in each bay, which will make sure that you're controlling your humidity level. And then we have this seal around the entire bay.
Yeah.
So it's just a compression seal. Once we close that, now we're in a good sealed, humidity controlled environment. It's important for model materials, but it's super important for PVA.
Right, and I actually have a spool of that here that I took just out of the machine. But
Right.
so this is our PVA spool. Let's talk about like a little bit more on why is it so relevant for someone. So this is how the spool looks like, right? It's got this central hub that Dave was describing. The hub itself has an RFID chip and also the desiccant pack, right?
Correct. So the RFID chip we use for material identification, and we also use it for material tracking.
Yeah.
So as we're printing,
That's the hub.
as we're printing, we're writing to the chip to track how much material is left on the spool. That way we can give a warning to a user when you shoot a print to your machine if you have enough material to complete that print.
Okay.
You can start it,
Right.
and it will just pause once you run out of material, and you can.
Yeah, but it's always annoying when you hit print, before leaving the office and you come back to a
overnight print. Yeah, absolutely.
Okay. And then, so talking about like the fact that PVA is rather sensitive to humidity, and I shouldn't even be doing this, right? You should be always having that.
That's true.
Either on the base or on the bag,
Right.
the Mylar bag. Right?
That's true. So, okay, so we wanted to go with PVA because PVA is a great user experience for the dissolution process, and that's because it dissolves in tap water.
Yeah.
So you don't have to use any kind of real agitation or solution, right? It's very safe. But the things that make it great in that respect make it a real pain to actually extrude it.
Yeah.
Because it just always wants to absorb moisture. It's a very dynamic material, and that's really the reason why we had to close it. And of course, we experimented both with other printers and on this printer with an open system, where this was subject to to the atmosphere essentially, and we found that we just could not consistently print it well.
If it wasn't enclosed and properly controlled.
Right. Because there's just no way to know and to compensate for once it's absorbed moisture.
So actually, I have a few examples here of those prints with supports. So as Dave was saying, we're using a PVA in order to create the supports for the parts. In this case, this is a cloth that one of our designers, Andrew Lasketel, designed here. It's pretty cool print, pretty complex for that as well. But as you can see, it requires a lot of support. So the support material is going to be these yellowish, kind of chewy parts, right? And the material itself, or the print material, the model material, is going to be that gray material there. And then, after I finish my print, I just dunk it in water and get this rather interesting bit. Here we go, like claw part. So it's what people call sometimes print in place, right? All of the components are printed in a single go. As you can see, like here are the two items, right? Before being dissolved, after being dissolved, and the fact that you have that very tight tolerance that allows you to have the mechanical properties of the part, the gears that actually interlock with one another in order to provide that clamping action. It's kind of a really nice print, but as I was preparing for this webinar, I also wanted to have a go at the support material from other printers and ours. So I ran the same print in this case, and I'll show you guys some of the details of it. This is the extruder that Dave was describing before. I run it both in our machine and in a desktop machine. A competitor with a specific heated build plate, but still an open PVA or material bay, let's say.
Open, yeah.
And what ended up happening, so method, it completed really nicely. You can see how smooth all of those details are. You can see kind of the circles that the printer did. All of the surfaces are super flat, even those very small details like those internal shells and internal ribs are very clearly defined. But, and I think, correct me if I'm wrong here, Dave, but I think what happened on the desktop was that the PVA, since it had been exposed for a little bit to the ambient, it started to glue on itself, and it prevented the material from flowing into the machine.
Yeah, and it looks like you get kind of a little like sputtering sometimes.
Why is that sputtering?
Yeah, so sometimes if PVA is left out and you're running it on a total open system, you actually hear like a hissing, and that's essentially you're just boiling the moisture out of the material.
Yeah.
But that that wants to expand and essentially does bad things in extrusion.
Okay. Yeah, I mean, I think it's been really interesting to see like how much does that affect that. It's kind of multiple systems at once, right? Having the control over the materials, having the controls over the prints, and what it comes down to, and we'll have some examples here, as you can see now in the deck, talking about specific parts, right? I'll start with this one that's kind of a very straightforward sort of gear that I made. If you want to hand them over. So I printed the same file in both machines, right? A desktop one and method. And well, as you can see in the picture and now in the image here, I have both of them. Both of them are the same file, but essentially in one I've got it so that the bearing slides easily. So I'll bring it to camera in just a second. But so here's my bearing. It's a little rusty also, but so I just nest it in, push it in place, and it lands nicely in that print, right? But in this one, as nice and clean as the surface might seem to be, there's a little bit of distortion, right? That distortion prevents me from actually nesting. Let's see. Yeah, it's still not gonna happen.
Yeah, it's interesting with this one too, because I looked at it earlier, and you can see it's really not that it's a circle that's too small, it's that it's an oval. Right, because
exactly.
You actually do have clearance. And
so I don't know, I hope that you guys can see there, but it's like, if you look at it dead on, you see that it's not a perfect circle,
Mhm,
right?
mhm.
Why would that be happening? What's the deformation? Where's it
So,
coming from?
I mean, probably gantry,
Uh-huh.
maybe belt tension,
Right.
or just not great consistency, machine to machine.
So it goes back.
Frame.
maybe
It's
to
really a
the frame.
combination of,
Okay.
of everything.
Right.
Mhm.
And then I have another one, and you were talking about these two as well. Here,
Mhm.
I'll bring it to camera just a second. But the same idea, right? So we printed the same print in two systems. So our system method, in this case, it's kind of this kind of toothed block, and all there is, they are all only like flat surfaces across well, all of the body,
Mhm.
and all there is that there's a point. It's 0.2, so it's 200 microns tolerance between each part.
I think
And-
it's 50 microns, 2,000.
Oh, sorry, yeah, you're right. 50 microns, so even less than that. And the parts just, slide in together.
Mhm.
And then if I take my desktop sample here, it seems pretty tight at the beginning, but then as I'm trying to push it in, there's just enough of, I'll bring it closer. Let me do this one more time. So I'm sorry for the zipper sound, but I think it's kind of cool sometimes. So this is our method print, right? And if I bring it in here, and here we go, lining all of the angles, and it slides in place. And on the other print, it looks rather smooth, so it's hard to tell that it's not going to work at the beginning. But as I try to line it up, let's see. Yep. So
Yeah.
there's just that little bit of excess plastic, right? And you can see it here, where just that little bit of extra drooping.
Yeah,
or
right.
How do we call
So
it?
yeah, I think it's a combination between
Mhm.
between like layer uniformity.
Mm-hmm.
There's a little roughness in the horizontal plane as well.
Yeah.
And I think the corners are a little fat, kind
Right.
of. So as you come in and you slow down and then you accelerate through a corner.
Yeah.
You need really good controls to control your filament bead width.
Mm-hmm.
And I think just from that being, you could actually see, if you look, that's kind of fat right there. Not sure if you can see that.
Mm-hmm.
But that's really, I think, going to block you. So unless
Yeah.
you were to post-process this
Yeah.
with like machining or sanding,
Mm-hmm.
you won't be able to get a real assembly here.
Right.
Mhm.
And then going back to the reasoning, and then going back to our deck here. So we do had the plan to create all of these systems. We had, let's say, all of the blueprints and then the components. But then it was also about the time that we spent testing them out, right?
Yeah,
So how does that affect, or has affected our development here with Method?
Yeah, sure. So, we have the professional in mind with this printer, and that means you need really high reliability in two senses. One, reliability that your print is going to complete. So if you leave work and you want your print to be complete the next morning, you start it, you want a high success rate, that it's going to represent your intended part, right?
Yeah.
The other thing is reliability just over time, over the lifetime of the machine. So we test right like today. We have 110 machines running 24/7.
Okay.
A lot of that testing, the high scale testing, really started in April of last year.
Wow, so it's a full year of just testing.
about eight months or so, and
Okay.
that's production representative testing. We'll have accumulated north of 200,000 hours now, and we'll continue to run those machines even post ship.
Yeah.
So we can test things like firmware improvements, toolpath improvements, additional materials, and all the machines are set up with our kind of internally developed data acquisition system.
Right.
So we're able to see stats on how those machines perform. Every morning. Every morning.
That's gotta be a fun email or call.
It's hugely important because you can make a firmware change, print another 10,000 hours across 100 machines, and you can see the effect of that change.
Right.
And it's really really important to do that, of course, before before the customer finds these things.
Right. No, of course, I mean, naturally. But then, I also want to keep in mind that we want to open the floor for some questions. But I'll talk a little bit on, specifically what do we mean by this new category that we call performance, right? When we say that this is the first performance 3D printer. And I believe that what we were trying to do there was kind of create a space between industrial and desktop systems. So we know that industrial systems are great for precision, great for reliability. They give you that result over and over again, and it's a very accurate one for that. And on the other hand, we have desktop systems that we know a lot of. So like the Red Plus, they're super open, super friendly, user-friendly, focused on the experience. That tend to be like also more accessible for many reasons, right? It's not only the fact that the price point is lower, but also the fact that any user can approach them. And in a way, we wanted to create the best of both worlds. And there's certainly a technology barrier there that we had to bridge. It wasn't just us increasing or incrementally adding features to our system, but actually adopting features that are not available, many of which you've seen that are not available in desktop systems, right? You'll never see, and I promise this is the last time I bring this guy over, but you'll never see a desktop system with this type of finishing, or sorry, the bones even, right? So you see, like just the level of complexity of the parts is something that's quite hard to do at this level, and then let alone mixing it with like that openness, that easy to use experience for the user. So that's, I hope that sort of clarifies that question around what do we mean by performance. And then moving on, we also wanted to say, like, okay, what is the high-level takeaways for the machine, right? What are we trying to focus on that we think that, sometimes it's done well by desktop systems, sometimes it's done well by industrial systems. So in this case, it's four things, right? You want to have material control, you want to have the print environment control, and you want to have accessibility, and you want to have like an accessible or a good enough total cost of ownership, right? More often than not, industrial systems do give you that material control and that print environment control, but, they are not that accessible. It's usually gated by a technician. You have to be heavily trained to use them, and it tends to be rather expensive, right? You're talking about $20,000, $30,000 at that. And then on the desktop system, they are really accessible. They tend to be have a lower price point, but then they lack that level of control with the material, with the actual print environment. What we talked about with the PDA, the material base, the rigidity of the structure, that ultimately translates into a not so good machine. Of course, there's many people that argue that if you keep a close eye on a desktop printer, it can run rather nicely, which is true, and I agree with that. But our goal here at MakerBot is to provide or to create an experience that doesn't require you to be taking care of the machine every print, and kind of calibrating it over and over, but rather getting consistent industrial quality results, right? So with that, I'll open the floor for questions, and Allison and Anastasia are doing a great job back there keeping track of us. But yeah, what are people saying?
We have lots of questions.
Good. Hello, the internet.
First, I would say, do the extruders have metal or plastic gears?
Oh, that's a good one.
Yeah, so both. They have the drive gears that touch the filament and push the filament down are metal. They're hardened steel. But the drive gears themselves, the 19:1 gear reducer, is mostly plastic. It's a very high strength, low friction plastic that makes for an efficient gear train. And then on the carriage itself is like a bronze gear.
Can you say when the ship date is?
Ship date. I think so. We're taking pre-orders now. I don't want to commit to the ship date, but if I'm not mistaken, it's by the end of Q1.
Yeah, just to start shipping in Q1.
Yeah, start shipping in Q1. So it should be coming in like the next, technically 4 to 8 weeks, right? Yeah.
What is the surface on the build plate?
Oh, right.
Yeah. So it's actually a proprietary surface, but it's a polycarbonate. It's a type of plastic.
But it's replaceable
It is.
as well, right? So
It is. You can replace. I mean, I believe we're selling this either as an assembly, if you just want to buy the assembly and have extra build plates, so you can take out parts. And
how easy is it to damage it, do you think? Or how many prints will it last?
So, I mean, the assembly itself will last really like infinite, you know.
I'll just flex it again because that's really cool.
Yeah. the build surface itself. I mean, I would think it would last a year based on the number of prints that you do.
Okay.
Especially if you're kind of careful peeling off.
Or just
print
like
longer.
flexing it till it comes up.
Right. Yes.
All right. Cool.
They were wondering about tuning the printer. What does it take in terms of out of the box, and then how much do you have to fine tune for optimum print quality?
So that's kind of what we were
question.
touching on, before, that idea of enabling you to be as hands-off as possible. And I'll talk about the first run experience, out of the box experience, right? So it's about, I'd say it has taken me, because I've done a few of them already, focusing on the UX side. It takes you about 20 to 30 minutes to complete the setup. So, and that is from me opening the box and taking the machine out of the box to having it running, right? You go through connecting it to the internet, updating the firmware, and then the calibration, which we were describing as, the tool heads. For the first time, they'll just run an initial calibration for them to know their position in space. That takes about 5 to 10 minutes. And then, I don't know, how often would you have to do?
So you only have to calibrate at the start, so or any time you take out an extruder and put one in.
Okay, yep.
And what about fine tuning, like for optimal prints?
Yeah, so we're launching with a balanced print mode, a high quality print mode, which will be basically lower layer height. It will take longer to print, but if you're doing like a small, fine detailed presentation model or something, you can do that. Everything we're showing you today is on the balanced print mode, so you can expect to get shapes like this with balanced print mode.
And it's already quite something. This is, I know I keep talking about this one, but I really like it. Just like, the smoothness of it. So I've tested two surfaces, that one that's like wavy and smooth, and then this one with the diamond pattern in it. That's also really kind of trippy. I could stare at it for hours.
Yeah.
But that's with our kind of standard.
That's the standard balanced.
Okay.
And then we have a high fill print mode for if you need a high strength, like functional part. We really don't, there's really no need to get under the hood. We do allow you to go into custom settings and make changes if you like. But something else that we're doing through these hundreds, through the 200,000+ hours of printing is not just testing for reliability. We're changing print settings, and we're measuring parts. We're creating print quality reports. So we're really doing that for you, and really urge you for best results to use one of the preset settings.
Cool. I'm getting a lot of questions about materials.
Uh-huh.
So let's start with just what materials can you print on currently?
Sure. So most of what you see here is MakerBot Tough, which is a material that is based on PLA, but has additives to have mechanical properties in line with ABS. Actually, an impact strength a little higher than ABS. Right now we have MakerBot Tough and we have MakerBot PLA. Those both print with PVA support. We're also tuning PETG, which is another nice option. Prints at a little bit of a higher temp, has good toughness.
And it has also some transparency to it.
Right, so it's think plastic water bottles.
Correct.
PETG. Yep. And that will print with a different support material, but still a water soluble support material.
And that's something that we're working on for the future?
Yeah, so we expect to have that out within about a quarter of shipping. And then we have the levers on this machine. We have a roadmap that goes beyond that.
Cool. People are definitely curious about what the next materials are.
So that's, I guess that also that heated chamber enables you to do other stuff in the future if you needed to, right? Just to take people who know, well, could imagine what that could be used for. Eventually,
Yes.
maybe. Yeah.
Absolutely.
And then also for the wheels that you have for filament, are those proprietary, and can you use third-party filament on this printer?
Yeah. So yes. So these are proprietary. They're made to fit within. They're made to fit well here. They have an RFID that interfaces with the electronics here. So if you want basic, it's also assisted drive system here. So you put filament in, it runs it up to your extruder. There's a switch in here that tells you when you run out of filament. So these are essentially the reasons to use our proprietary material, as well as just our quality control, and that there's hundreds of thousands of hours of printing that we're doing are all with our materials. However, we don't block the use of third-party materials.
So there is a port which is possible, but I mean, again, we've talked about the fact that it's actually kind of in order to guarantee those results, you really want to have that control over the material, right?
Yeah.
So keeping those inside of the base, so you have an external port where you can side load material if you wanted to. We really encourage our users not to, because we want to provide that full experience. I know that there's people who will challenge that statement, but it's true. I mean, I've seen it, and you've seen it, in some of the samples here. By having that extra control over the materials, and that is by using the materials that fit in those drawers and that are sealed and controlled with the humidity and the temperature sensors, you do really change the output of the machine.
Right.
Cool. Can you just walk us through how it feeds the filament in?
Oh, sure.
Because I know where the chambers are, but...
Yeah, so let's see. I actually have it had it prompted ready. I hope that you guys will be able to see it. But you have the bay here, the machine. You have a touchscreen. We didn't touch on the fact that the machine has a touchscreen. So unlike the Red Plus, this one comes with a 5-inch capacity touchscreen. You go into the material area, and then just hit load. It'll ask me to present the machine with the spool itself. And as Dave was saying, the spool has the RFID chip embedded in. So I'm just able to nest it in. The printer will detect it, and as soon as it does so, I can just, let's see. So it'll start heating the extruder, and once it's done heating that, it takes about 10 seconds. So right now it's at 160, 170 C. It takes it up to 220, and once it's finished doing that, it'll auto load. So that's another reason why you'd want to use the material base, right? Because that really automates the process, and just once I started it, I just close the bay, and then the material will start to be loaded on the side, and then that's all there is actually. So it's pretty straightforward. I like the kind of automation of it all.
Cool. We have some questions about the heated build chamber. How hot can it get?
So right now, for PTG, we're running at 55 C, and that's probably like the as high as we'll end up running it.
Okay. And how long does it take to heat up?
40 C. So first you can basically keep it warm. You can like preheat it if you're just continuously printing. But I think it takes,
I think it's about like 3 minutes or so.
something like that. I believe it's less than 5 minutes to heat up. So we do go through a fast heat up cycle where we have both heaters full on and the fans full on, and then we slow that down when we're in kind of temperature maintenance mode throughout a print.
Cool. When you switch between heads, do you purge the nozzle before printing?
Yes. Yeah. Great.
I'll bring it to the camera, but you can talk about it.
Yeah. So we do. We do a retraction. So once you're done printing with an extruder, you pull back on that material. We cool that extruder because we don't want it to ooze. And then when we go back to that material, we'll go over to this purge tower. We'll just do a little shape here, and you can move around this purge tower in MakerBot Print as your part geometry permits. And that basically like pre-charges your extruder, so you know exactly where your filament is, and that gives you a good start once you go over to the island.
For me, it's amazing how, because I've seen it in other systems, how clean even the purge tower comes. It's not supposed to, right? It's supposed to catch those defects, but you can see like it's just that little line. Those little lines are the extra oozing, and I think that comes back to the level of control that we have as we're extruding. So it's not really using a lot more material than it needs to, but you still have that feature to clean up and reset and also every time. Yeah.
Cool. Which leads me to my next question is, what's the software and how customizable are like prints?
Right. So that's our MakerBot print software. It's completely free. Anybody who's used MakerBot before knows that it's super user-friendly, and as Abe was saying, we actually offer preset print modes for users to benefit from, specifically 3 of them: balanced, min fill, and high quality. You can get under the hood and change all of the settings if you want to. We actually take a long time into creating those presets so that you don't have to, basically. But if you want, you can change anything from the number of shells, the infill percentage, the number of walls, the roofs, even some temperature settings in it. But yeah, in future webinars we'll probably be talking more about that specific process around the software itself. But it supports over 25 native CAD pile types, so that means you're able to say, and we're working on that plugin for SolidWorks, right? You can directly from SolidWorks hit print and get it. And it goes back to that story of the fastest CAD to part, right? How do we guarantee that you're moving seamlessly from your CAD model into your printed object?
Cool. How long does it take to clean the support material away?
Okay.
That you want to say? Or?
Yeah, so it's hard to answer. I mean, you do have to soak it. It's not something that you just run underwater and it disappears, But basically, PVA softens. Really, the time is dependent on like the quantity of PVA and how much surface contact there is. So what you'd see for a part, a part like this,
probably going to 4 hours. Yeah. So I'll bring them closer.
Yeah, a part like this, around 4 hours. If you're really, if you're in a rush, you can essentially put this in a tank, let it soften, and then like peel the material off. Then you could certainly get your finished part a lot quicker.
Yeah, so I'll say that too. Like the biggest chunk of material, like let's say all of these big walls, will dissolve the fastest, and then the material that's right up against like the contact layer that we call, it's going to take a little bit longer, but it goes back to the fact that our PVA material is rather sensitive to humidity because of that, right? We want to actually expedite the time that it takes for you to dissolve the material. There's other materials out there that are not as sensitive to humidity, but that also means that they take much longer to dissolve.
Right.
So
that's right.
Yeah.
Let's see, what else do we have? People are curious about the other printer that you used for comparison.
So I've used a range of them, right? As I said, we were trying to do both industrial and desktop systems. We have our own desktop systems available at Rep Plus. I, of course, I'm not going to be name dropping anybody here, but we wanted to be, consider all of the, main options out there that people would be using, right? All of these desktop printers that claim to have these precision levels, that claim to have these industrial settings, which is more often than not the case, right? So it's hard to claim that you have a professional system, an industrial system, if you don't protect the material, if you don't actually control the print environment. So it was a range of them. I cannot tell the specific of them, but yeah, it was like the main desktop options that we have available. And of course, having access to Stratasys, we had a few industrial options to test against as well.
Cool. And then those, did you try and print those out of the box, or did you tune those printers when you were working on them?
I did both. And that's also kind of one of the pain points that we wanted to solve for, right? We want to offer a machine that's not meant to be tuned, but rather works out of the box. Many of these machines are actually, they come in the box with a glue stick.
A little card.
I mean, a machine that comes with a glue stick on the box, I'm not saying who, but claiming that that's a professional system is a stretch. But yeah, we actually tuned for it. We tried to give it a fair opportunity to shine, and sometimes they provided good results. But again, it's that issue that we're trying to solve, the fact that we don't want you to be spending 5 hours before you print or between prints trying to tune the machine, trying to reset the nozzles, recalibrate everything to get the consistent result, but rather that you were able to just print and get going.
Yeah, and the MakerBot was not, in terms of the MakerBot, that was not dialed in. I believe you have just the beta, the production beta units.
Yeah.
And it just balanced print mode.
All right, we only have time for a few more questions. People are curious about, can you use this for 2-color prints, and is PVA required for supports, or can you do like a 1-filament system?
Yeah, so you can do breakaway support. I'd certainly encourage for using PLA, just because then you're not bound by geometries that work with breakaway supports, and you get a much better kind of surface finish on the bottom. So this is the supported floor. So you can see you get a very good surface finish on the bottom of the part. And then for multi material printing, yeah. So right now we're shipping with the machine comes with 1 model and 1 support extruder. But we are in the future going to support running with 2 model extruders, in which case you could use dual model printing.
Yeah, so you basically have 2 of these one in order to print with 2 colors. But for now, the goal is to provide, again, something that actually enables you to print without compromising the geometries that you might use, and easily and fast. So.
Yeah, we feel this is the primary use case, but yeah, we definitely, dual material is definitely something coming on, that's going to be coming online.
I definitely have a question about airflow filtration and like keeping particulates out of the air. Is there anything in place for that?
So the machine is enclosed, so that reduces in general the particulates from escaping. There's bellows. So we have enclosed system. Not sure if you can tell, but this is enclosed. There's a window back here. And then we have a lid. The lid does have air vents, but there is bellows to create a pretty well sealed environment.
And on that note, I think that we've all seen that report. The report, the test that was conducted last year and the year before as well. We were part of it, and it was impressive to see like how our machines perform, and the fact that specifically because of the fact that we don't currently support ADS. Which is the most prone to having those volatile compounds. Our machines, outperform many others because of that. There's nothing much to be detected when you're printing PLA and TUF, for that matter. If you compare it to ABS, so yeah.
Cool. I think that's about it for now. We have some smaller questions, but they can be asked later.
Oh well, so yeah, for sure. So if you have any questions, we do have our email here, hello@makerbot.com. We'd really love to hear from you guys. I think that as always, it really helps us create more content if you guys reach out and give us more questions to have ideas around what would you like to know. If it's more about the method itself, we're looking to do like a more in-depth overview of it, like with samples, more prints, kind of getting a little bit away from the systems and into the use case. So yeah, feel free to reach out, hello@makerbot.com. Thank you all for watching, and thank you for all of your comments. Yeah, if you have any questions additional, or if there's other topics that you would want to see covered here, hopefully we'll be talking more about some CAD tips and tools, some of the interesting things that happen once you start mixing PVA or actually using PVA as a material in order to give you like that extra level of freedom when 3D printing. But yeah, feel free to contact us. We're really happy and excited that you guys are reaching out. And then yeah, I think that's it. So
thank you very much.
Thanks again. Thanks, Abe. And yeah, we'll see you next time. Thank you.